Hey guys, my name is Adrienne and welcome to Organic Chemistry 1, Part 8 of these recorded sessions. Today we'll be going over, for most of y'all, Chapter 8, but in general, we'll be going over alkyl halides and elimination. So here is our agenda for today. So alkenes, elimination reactions, and then more specifically E2 reactions, and then alkyne synthesis. And again, as always, I'll have the topics up on each page we do. So feel free to scroll over and you know, find what you most want to discuss. So with that being said, let's hop on over to alkenes. So alkenes, we know are double bonds, right? Anything with a double bond, not big deal. But the biggest thing with alkenes is that they have restricted rotation, right? They don't rotate 360 like alkanes rotation. And we know from hybridization, we know that double bonds are sp2, um, trigonal shape, right? With 120 degree bond angle. And with that, with alkenes, they make a great point of view for molecules because you can tell which ones are more stable just by looking at them. And that's because of the classification. So we have just a regular alkene, and then we have mono, di, tri, tetra, right? So alkene, just a regular double bond, right? Mono has one R group, di has two R groups, and tri and tetra, so on and so forth, right? And of course, the rest of them are just, hydrogens. Okay, and I mentioned stability because, and I'm going to color this because the more you go this way, the more substituents you have, the more branches the double bonds have, um, stability increases, right? Increases. So it's kind of like carbocation because we know carbocations prefer those with more substituents like tertiary over secondary over primary, things like that. So kind of same concept, but instead of tertiary or primary, secondary, it's tetra, tri, di, mono, right? So stability increases that way. So that's that. Nothing too crazy. We know all of these. And I guess just to mention that since they do have restricted rotation, that isomers tend to be classified as diastereomers. Because since we can't rotate it, all we can do is break it off and move it somewhere else, right? So that's kind of the concept. So, like for example, this one, we can't rotate these back and forth, right? We have to break this one apart and then move it up here, and then vice versa. So that's kind of it with that. So now let's go on to the elimination features, which is what we'll be focusing more on this lesson today. So elimination features, we know from a couple videos back, or I think one or two videos back, we know that elimination, and I'm gonna do this in a different color, is that loss of two sigma bonds to gain one pi bond, right? We know that. And just a couple examples of elimination reactions, and we saw this a while back as well, is that you know elimination of alkyl halide and dehydrohalogenation, which is pretty much the same thing. And what these two have in common is that, and then again, different color, beta elimination. So this is what you should be thinking every time um, you talk about elimination, right? So let's say we have something like this, X over here. this one over here, this carbon where the halogen is going to be our alpha, and then whatever the one that's adjacent to it is going to be the beta, right? So now we're going to have our beta elimination. So let me change another color. So this is going to be eliminated, and then for beta, we have a hydrogen here, right? That's going to be eliminated. So that's where the pi bond forms, right? So we have our two loss of two sigma bonds, which is the hydrogen and the halogen, right? And then get our one pi bond. Super easy, right? And now another important one with elimination is the Zaitsev's rule. Oh, Zaitsev's rule. And this is a different color because it's important, right? It's that in elimination reactions, major product um, has the more substituted double bond. So, meaning that tetra is prioritized over tri, di, um, mono, right, or nothing at all, right? So that's Zaitsev's rule. So, and of course, like we saw a couple videos back, there's anti-syn, cis-trans. There's also going to be Zaitsev versus anti-Zaitsev, which is going to be just backwards, right? But for the most part, the most common is going to be Zaitsev's rule with elimination because, again, like we said, the more you go towards tetra, the more stable you are, and we always want to be as stable as possible, right? So that's where that comes in. So Zaitsev's rule, very important. I'm sorry, right? So with that being said, our last little bit for alkenes is nomenclature. Again, you guys are probably already experts on nomenclature, right? IUPAC is the same, find the longest chain, blah, 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 number it, name it, alphabetically, things like that. But now, instead of cis-trans, we're using E and Z. So E and Z. So Z is pretty much the cis, and then E is pretty much the trans. But the difference between these is that while trans and cis describes the whole molecule, E and Z describes a double bond. So wherever the double bond is, let's say the double bond is in the fifth carbon, E5, right? So things like that. Um, describes double bond. And let's do a little example. E, we said is trans, right? So you're going to have something like this, R, and then Z is the same, so we're going to have R, things like that. And the big thing about this is that you cut them in half, right? And then in half again, right? So, and then you find a priority. The priority is always going to be the biggest R group or the biggest group there. So obviously this is an R group. We only use R groups, so these are the biggest priorities. So this one's going to be going up, and this one's going to be going down, right? And then same thing over here. This is R group, this is R group. Both are pointing up, right? So that's cis. E, Z. So same thing with kind of like the R and S. You find the biggest molecule, right? But instead of doing it atom by atom with these, you go by the whole thing. So if this was, let's say, like oxygen versus a methyl group, obviously the oxygen is going to be here, right? Or let's say this H, instead of this H, this is like a bromine versus this R group being like a methyl group. Bromine will then be our priority, right? So making this cis. So things like that. And with that being said, I think, as always, it will be better to practice. So let's go ahead and practice some of these. And I think, yeah, I have a couple questions for um, each of the topic we talked about. So let's say we have these. So label classification of double bond. So let's say we had this. So label all the double bonds, and then let's do this. How many unique beta carbons for these two molecules? Okay. So take a second, pause the video, and come back with your answers. Okay. So welcome back. So label classification of double bond. This one, what do you guys get? Tetra, right? This one, di. This one, what do you guys get? Di, right? So now let's go one step further and identify if they're E or Z. So this one, what do you guys pick? So for this, you should have had um, E, I mean E for trans, right? Because what's the priority group? We said we cut it in half, right? So this is the priority, and this whole thing is a priority, right? Because it's obviously the bigger side. So it's this one's going this way, this one's going this way, so opposite ways, E trans, right? So di, what about this one? This one has no E or Z because there's nothing on this side, right? These are just H's. So um, we need to have something on both sides to be able to compare it to E or Z. And A does not apply. What about this one? Right, there's only two. It's only two, so this one's going up, this one's going up, so Z. So easy as that, right? And let me change the color so it's not too green on your screen. Oh, okay, how many unique beta carbons? And this is where the beta elimination kind of comes in. So in this case, actually, I forgot to put this. So yeah, sorry about that. So redo your answers real quick. Or actually, let's do this one. So in this case, we know in elimination, um, we take out the best leaving group, right? Now, obviously, the best leaving group is this Br, and we said that this the carbon it's bonded to is going to be the alpha, and all the adjacent ones are beta, right? So this is going to be beta, this is beta, this is beta. So with that being said, are they all unique? We have three betas, so that means we have three positions we can eliminate from, right? We can have three choices where that double bond can be, but we're asking for unique. So we should have only two unique beta carbons because these two over here are exactly the same. B1, B1, B2, right? So, and then if you guys are curious, we have three choices for the pi bond to go, and it can be between these two over here or over here, right? But where will it be more preferable? On either of the B1s, right? Because that's the most um, stable. This is gonna end up with try, right? Either over here, try, because you'll have one, two, three, and this one as well. One, 2, 3. So B1 most stable double pi bond. Most stable pi. Just extra info, right? Okay, so now let's do the same thing for this first one that I forgot the halogen on. So we said halogen. This is going to be our alpha, and then our beta, 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 and then again for unique, we have 1 here, and then 2 and 2, right? So we have 2 as well, 2 unique ones. And then let's just for fun, let's label the most stable pi bond. So we can either have it over here, we can have either have the pi bond over here or over here. So again, either actually all of them are the same, right? If we have a double bond over here, we can have 1, 2, 3. If we have it over here, we can have 1, 2, 3, and then so B2 will be the most stable. Most stable pi. So things like that. So you already know how to do elimination reactions, right? Where to put that pi bond. And again, this is all because of Zaitsev, the blue, right? Where the pi bonds are. Okay, we have a couple more, and this is naming. So, okay, alkene nomenclature. So we have 3 here. So just name them. So as usual, we can have cyclic 2, right? 4. Did I do that right? Yeah. BR. Okay, so take a second, come back with the answers. Okay, let's see. You guys should have gone for the first one. And this is, it'll be easier with answer choices, but, don't forget that you can do R and S and all that stuff. E and Z, things like that. So you should have gone S3. Oh, this doesn't even S3, bromo, 1 methyl cyclohexene, right? And ene because of that double bond, right? And how did we go around this way? Again, the cyclic is the longest parent chain, right? And we said that the double bond or the parent chain has to go through the double bond. So we went 1, 2, 3, 4, 5, 6, right? And then this is a substituent, this is a substituent. And you guys might be wondering, why didn't we go B first? Well, if we did, we would have gone 1, 2. Our double bond would have been in the 2 position instead of the 1, right? So again, our parent chain is the double bond, right? So we want that double bond to be the priority. We want that to have the lower number. So let's do this one. This one guys should have gone again. Don't forget your S, R's and Z's and E's. Z2 bromo. This one's more straightforward. 3, 4 dimethyl 2 pentene, right? And if your double bond isn't on the first carbon, then you have to indicate it, right? The double bond is in the 2, but 2 carbon. It starts in second carbon. So things like that make the difference between alkanes and alkenes, and you'll do the same thing with triple bonds, pointing it out where it is, things like that. But everything else is the same. And again, the ending is the one that changes. Ene for alkenes, anes for alkanes, ines for alkynes. So, right. So that's all. Nothing too crazy. Just pay attention to just pay attention to these two. Because they're part of the naming process too, right? Okay. So, with that being said, let's go on over to the good stuff. Elimination reactions. And same thing with what we did for substitution reactions, right? They're pretty similar. We will have two rows, or I mean columns, I guess. E oh, that's supposed to be E1. Okay, okay, E1. So first things first, and again, similar, very similar to the substitution. E2 is gonna be your bimolecular, molecular, and to save room, it's gonna be one step. Second order, one step, right? Same thing with SN2. It was second order because of the two, right? So second order and one step, and the rate, there was also rates. Same thing as SN2. Um, rate is both the alkyl halide, but this time instead of a nucleophile, it's a base. Base, right? So that's the rate. And now, transition states, things like that. Um, but the reactivity here prefers tertiary, secondary, um, primary methyl, right? So tertiary is the big one here. So that's the only switcheroo from SN2. A lot of rhyming today. So that's the only opposite of from SN2 because so far these three appear exactly the same as SN2, right? Well, except for the base, I guess. But so favored by strong bases, and same thing with SN2, right? Strong nucleophiles, strong bases as, and these are some of them, DBN. These are the more usual ones, DBU, and then it also has solvents. Same thing with SN2, aprotic solvents preferred, right? So now you guys probably, you know, E1 is pretty much exactly the same as SN1, uni molecular, first order, right? First order two steps, and rate, it's just gonna be, oh, it's just gonna be the alkyl halide. So nothing too crazy, right? Nothing too crazy, and it's actually nothing too crazy. And then again here, probably the easy thing about elimination is they always prefer tertiary, so you don't have to worry about that, right? So both of the E1 and E2 prefer tertiary alkyl halide, right? Now weak bases, weak bases, which is pretty much H2O, ROH, things like that. That's pretty much what you'll see a lot of. And then again, protic solvents. And as always, um, the better the leaving group equals faster rate, right? So that's the same as any other reaction, right? And with this, we talked about a lot of comparing nucleophiles or substitution with elimination. And before we do that, let me point out some stuff, the important stuff. The rate is important, obviously. This is important. Pretty much all of these are important, right? So let's go to, substitution versus elimination. So they're not always going to tell you, oh, what's the elimination or what's the substitution? What's the SN1, SN2? What happens if they're all mixed up, right? So what happens if they give you, is it SN1, SN2, E1, E2. What do you do? So if um if it's if the reactant or the solvent or the base or things like that, if it's a good nucleophile that is a weak base, it's gonna prefer substitution over elimination. Okay? But if it's a bulky, non-nucleophilic um, base, it's gonna prefer elimination. And the easiest thing to kind of describe these is that bulky bases always elimination, nucleophiles always you know always substitution. That's kind of just what I go by, and it's not too tricky. And you'll notice that the good nucleophiles are very small. They're not bulky at all. So, um, and then for bulky, they're usually be bases. So that's pretty much go by the bulkiness, and you should be fine. You should be fine. Okay. So that's all there is for elimination. Nothing too crazy, right? It's actually I feel like less than what SN2 and SN1 had, because SN2 and SN1 had the full um backside attack, frontside attack. This is all whatever. This is all the same, because it's just elimination. We're just making double bonds. Nothing too crazy. So with that being said, let's do some practices. Let's do some practices. Practice. Okay. And I don't know if you guys are liking the whole like column thing. That's how I did it. But of course, you guys can probably do it much better in your own way. Um, with different colors, more colorful or things like that. I do a lot of coloring and stuff on mine. Um, or like if you want to jot more notes, like more detailed notes, things like that, feel free. I think that's the best way for you guys to like really remember this stuff. Like, you don't have to like cram it, because if you just have, little columns of everything, it's so much easier to study, right? You don't have to keep flipping the page or whatever. So here, find the product. Find the product of this one. And this is where you'll kind of see how different some of these reagents are. So find that one, and then I think I can fit another one. And then this one, which one's the least reactive in E1, E2 reaction? CL. Okay, that's it. So CL over here. Um, okay. Oops. Okay, let me review this. Okay, so take a minute, pause the video, and get back with your answers. Okay, so reactions, we know, and how do we know why? Obviously, it's elimination reactions, right? If we took off the title over here, how do we know that these are elimination reactions? Because this is a bulky base, right? Bulky base. So that's kind of how we find out why it's an elimination reaction. And this one is just a base in general, right? With the alkoxide and things like that, base. So we know these are elimination based on that. If we weren't told if it was elimination reaction or not, right? So with that being said, what are we eliminating? We have to look for um, two sigma bonds that we can take off and replace with a pi bond. So we know for sure this is coming off, and we have to look at the beta, right? So our beta is going to be over here, and our beta is going to be over here. What do you know is over here? There's no hydrogens. They're all methyl groups, right? So is it likely we're going to take off a whole methyl group to eliminate versus what is this? All hydrogens over here, right? So what's better? Taking off a methyl group or taking out a hydrogen? Taking out a hydrogen, right? So you should have gotten something like this, right? So nothing too crazy. And we can't make a double bond here because first of all, it doesn't have the beta hydrogen, right? And if we take this out, the methyl group is going to be a whole different molecule, right? And we don't want that. So, and what about over here? This one again, we have the alpha over here, and we have beta. So we have two beta, possible betas, because we have hydrogens over here, we have hydrogens over here, right? So you guys should have given me two products. Over here or over here. Where's the other one? Over here, right? So this is the products you guys should have given me. So which one of these is the major product? Right, major because this is a tri substituted compared to our minor, which is actually just di substituted, right? So we want this one. So let me change to orange. There's too much orange. Um, okay, right? So that's all there is to it. And we did this major because what's the rule? Right, Zaitsev, right? Okay. Now let's do least reactive in E1, E2 reaction. You guys should have given me this. And why? Very simple answer. Very simple answer. Because, again, this is our alpha, and our betas are over here, right? Do our betas have any hydrogens? No beta hydrogens. And this is alpha. We have beta hydrogens over here, hydrogens over here, hydrogens over here. This is our alpha. We have hydrogens over here. This is our alpha. We have hydrogens over here, hydrogens over here. So this is the only one that doesn't have any beta hydrogens that we can take out. And same concept as this first one, right? We're not going to take out methyl groups, right? So that's why you guys, this is the least reactive. This is actually um, non-reactive, right? So there's that. And I have a couple more for you, or I think just one more. Yeah, one more for you. So nothing too crazy, right? Elimination reactions are probably one of the more simple ones. Because, I mean, you're just making a pi bond somewhere, and that somewhere just has to be adjacent to wherever you took off whatever from reactions. So I guess let's level this 3. Find the reactant this time. So we're kind of going backwards. So we're looking for this that turns into this. So take a second, take a minute, pause the video, come back when you have the answer. Okay, you guys should have gotten something along these lines. And I kind of did it backwards, but that's okay. So something like this with an X, any kind of halogen, and a methyl group over there, right? And again, um, you know, we could have had the product or we could have had this as well, right? But this is our major or minor because our alpha is over here, but we also have a beta over here, a beta over here, right? So as long as it gave me this, you're good, right? And again, Zaitsev, Zaitsev, right? So that's all there is to it. And how do we know it was an elimination reaction? This is the base, right? Alkoxide, which is the base. So things like that. And alkoxides are just, negative charged oxygens. So nothing too crazy. Um, very doable. That's it. Now we said elimination didn't have a lot of as many stuff as substitution, but in particular we have E2 reactions are more special um, than E1, I guess, right? E2 because E2 reactions occur most often in the anti-periplanar. Anti-periplanar geometry, right? So that means it reacts in the lower energy staggered conformation. So going back to the Newman projections, right? We don't really have to look at it that way, but basically the base and leaving group are away from each other, right? From each other. So anti-periplanar just pretty much means anti. So this anti, we know anti is more stable, so it's lower energy, right? That's what they mean. And I'm gonna actually underline anti-periplanar, even though I didn't really say planar, but this is important. That's an important word for E2. And also, they have to be transdiaxial. Transdiaxial. We know that from the chair conformations. We know what diaxial means. We know what trans means. They're just opposite from each other, and they're both in axial positions, right? So let's say X halogen must be anti to the beta hydrogen. So the beta hydrogen is the beta elimination, obviously, right? So must be anti to beta hydrogen, right? And over here, this is where it gets interesting. Translate axial, and I'm gonna underline that as well because that's an important key term as well. And then I'm gonna pink this priority. Translate axial is a priority over Zaitsev. So think about it for a second. So we know Zaitsev is when we do the products, right? Like, oh, okay, we get the more substituted product. But it can't happen, E2 can't happen if it's not transdiaxial. If the elimination or if the molecule is not transdiaxial, the elimination won't happen. So if it doesn't happen, we're not going to get a product. So we don't care about di-sub at that point, right? So that's what that means. So trans-diaxial is important for an elimination to reaction, right? So let's do, and you'll see this in better in practice questions. So let's do some. And this is kind of like probably the more challenging, especially visually. Not visually even, more like kind of like realizing, oh, I have to take that into account type thing, because E1 and E2, we know like mono, they require, prefer tertiary over things, but E2, this is where people kind of like forget about. It's like, oh, oops, you know what I mean? So don't forget about it. So which of these protons is most readily readily abstracted under, and since we just talked about it, you guys are probably like on high alert, which is good. E2 conditions. So, and since we were talking about like cis trans, periplanar, we're talking about what else? Transdiaxial, why not a chair? We know what chair is, we know how to do the positions, things like that. So let's say we have a BR over here, right? And our options are HA, HB, HC, H, hold on, HD, HE, HF, HI, EFG. Oh, this is G. Oh, it doesn't matter, I guess. HH, uh, HG, I guess, right? Is it going too crazy? Um, HK, HJ. So hopefully that you followed along, but pretty much I labeled all the hydrogens, right? A, B, C, D, E, F, I, G, H, J, K. Sorry about that. And let's do this one because we have room. Find the reactant. Okay. Okay. So take a second, pause the video, try to read this chair, and come back with your answer. So I I said earlier you guys are probably on a high alert because we just talked about the E2 conditions, E2 reactions, and why? Because we know they have to be anti-periplanar and they have to be transdiaxial. So we know for sure that this BR is going to be eliminated, right? So now we're looking for something that's trans and that's an axial position. So this is our alpha, and despite all these options, we're only going to be looking at the adjacent. We're looking at this one, we're looking at this one, right? Our beta, and then our alpha is over here. So we don't care about the rest of these, right? So if you got confused where everything was, it doesn't matter. Okay, so now we're looking for something that's anti and that's anaxial. So this is, obviously, this is down axial. So we're looking for an up axial. Which one of these are up axial? Right, HJ is an up axial. Up right? So your answer should have been HJ. That's where the double bond will go over here, right? So HJ is the answer. Nothing too crazy. All you need to look for was opposite, and it has to be an axial. So now let's look at this one, the second one. Find the reactant. You should have gone what? Okay. So you should have gone something like this. And I'm gonna write over this, but a halogen of some sort, right? A halogen of some sort, and then same thing. So why, right? Why that in particular? Well, again, we know we need anti-periplanar and trans-diaxial. So over here, the double bond is over here, right? So we could either have um, we could either have the halogen over here or over here, right? To make that double bond. But you can see how this is actually going towards you, right? And we need something that's going in the back. So this is saying this group is going towards you, so that means the hydrogen that they're not showing, the fourth group is going to the back, right? You see this hydrogen is to the back, so we since the double bond didn't form here, that means this isn't gonna work, right? So that means if this is in the back and it didn't form here, this must be also in the back, right? Because that means that there's a chance that the hydrogen over here was going to the front, which would make these trans, right? And that's all there is to it. So if it didn't form here, we know that the transaxial wasn't being met, right? They were not anti-periplanar. Um, so if it formed here, that means these two over here, the beta, the alpha over here, and the beta over here are in that anti-position that we want. We want that anti-position. And this is where I was saying that transdiaxial is prioritized over Zaitsev because clearly this would have been the better Zaitsev, right? If we had made this a wedged, this would have been good. But since it's not, it didn't follow Zaitsev rule, something must have been up. So kind of like, taking that into account, though. What's missing over here? You know what I mean? And also, this will be a lot easier once you have choices because you'll actually see. Um, we could have had something, you know, you could have also have this answer choice that's just backwards, um, like that, X, H, or some deviation of these two. So either or is good, right? So things like that. So that's what to keep up with. And honestly, this is important. Take away from that. You know, don't forget that. Don't forget that. Okay. Okay. Now let's go on to our last one, alkyne synthesis, which should be really easy, because we know how to make alkenes, and basically we just do it twice for alkynes because we're just making um, two double bonds or two pi bonds, right? So two consecutive eliminations nations for two pi bonds. Pi bonds. Pi times two. Okay. Yeah, pi times two. So we could either have our starting materials could either be And you guys saw this in the thing, vicinal or geminal. And these are good vocabulary words as well. So vicinal is halogens right next to each other, right? And then geminal is halogens on each other, things like that. So they're in the same carbon. These are in opposite carbons, right? So, and they need stronger bases to eliminate. So, stronger bases. These again, and these also apply to E1 and E2. So, H2 or Na, KOC plus DMSO. So either this one or these. So you guys should be looking for alkyne. But the bit the giveaway is going to be vicinal geminal, right? And also it doesn't always have to be stronger bases. You can also have um they have to have two equivalent or excess to get through these, because if they just say one equivalent, then obviously you're just going to be eliminating once, right? So stronger bases times two or excess times two equivalent or excess, right? So that's what you're looking for. But let's do some practice. The hardest thing for alkyne, I think, is kind of visualizing it, because we know it's going to be a different video, but we know alkynes triple bonds are flat, right, 180, so they kind of look weird. But synthesis. So let's see. So something like this: KOC CH3 3 and DMSO, and there's an excess of both, right? So that excess is a good sign that's saying, oh, this will react forever, and so everything's gone, right? We are over here, and then two equivalent, and then this. Um, find the reactant. So of this. Okay. So take a second, take a minute, pause the video, and get me your answers. So for the first one, you guys should have gone something like this, right? So at first, what I do, I always like do it bent first, right? Because we know the double bond is going to be there's the only choice. But then we know it's a straight chain, so it has to be 180. So and then I turn it into something like, you know, like that or something. So we have one, two, three, four carbons. One, two, three, four carbons, right? So same thing, but this is the right one because it's all straight, right? So it's kind of just something that I do. This one I kind of drew it already straight, so it's whatever, right? That's really ugly, but you get the point. So pretty much same concept. You're just adding two pi bonds and making them straight, right? What about this one? There should be two and you can have chosen any halogens, any of the starting materials, right? So we have our geminal over here, which is we said one of our starting materials, or vicinal. So either one of these is good, right? So nothing too crazy. You guys seen these before? Seen the rules, seen I guess the steps that we do for, and it's the same for any other reaction. The only thing that I would say is that point out again is that excess to equivalent. What happens if it didn't say excess? Let's say it didn't say excess, then we'll end up with something like this. This is just one equivalent. That's a product with one equivalent, right? Same thing over here. If it was just one equivalent, our product would have looked like something like this, right? And a BR somewhere. So this is one equivalent as well. So things like that. So pay attention to those excess to equivalent, things like that. Just because it's a vicinal or geminal starting material, it's not always going to mean that we're going to have an alkyne, because it depends on how many of those reagents is available to us. Okay. So with that being said, that's all we have for today. Again, these are what we covered, and hopefully, next time you have any questions, have any problems, you come watch one of my videos, and hopefully you guys join me next time. I'll see you guys later. Bye.